This is GMAETS 41. You are welcome to this special class. Yes, very, very special class, which is dedicated to you, dear friends, always tuning in to this channel, and of course, many more that are yet to tune in. It's a great dedicated class. Yes. To our dear friends in Nnamdi Azikiwe University, Oka, you know, you're working on this experiment this week. Experiment focuses on damping simple harmonic motion. Damping simple harmonic motion. So simple harmonic motion where there is damping. Now, in the past less than 24 hours, I had actually carried out the live experiment on this. Yes, I carried out a live experiment on this to teach you, dear students, how you can run this experiment live. But again, during the live experiment, I explained that this experiment is quite tasking. We got this table of readings. You can take a look at it. We got this table of readings. Let me hold it so that you can see it very well. So this is what we got. Good. Through performing the live experiment. So now, I want to show you how you can get your values without performing the experiment completely. And of course, as it stands now, with the manipulative formula I am going to give to you, you can be able to actually carry out, you know, your works in order to get the table of values without actually doing the experiment. Meanwhile, please, as a loving warning, I always tell students, my reason of doing this sometimes, like giving out manipulative formula, is not in any way to make you become so relaxed and lazy. You know why? On the D-Day, it will be you alone, your experimental materials. Are you following, right? Your experimental materials, and of course, the question. You want to know how to carry out this experiment. So please make sure you watch the previous video. It's also a live class. Go under the live section of this channel. You will see the live experiment demonstrated and how we got the values. There were several messages that were sent to me. You know, oh, so please, is there a way we can work around this formula and other things? Because perhaps, you know, no one has actually done this to bring out anything, any work that could guide students. And by the way, before I move on, I want to commend the team of UNIZIC Physics Laboratory Works, you know, the team there that designed this experiment, because this is the first time ever that this experiment per se, has been brought out for the students in UNIZIC. And it's an experiment that is involving. You have to be engaged in it. And of course, I commend them. They did well. Now let us see the manipulative formula that will guide you to generate this table of values. Are you following, right? We have on the board theoretical equation given. The theoretical equation in your workbook is there. For our dear friends from many parts of the world that will be connecting to this particular class, please take note that this is the theoretical equation guiding the experiment. And in one of my previous live class, I had already explained the importance of theoretical equation, why students should not joke with it. So this is the theoretical equation guiding the experiment. This is ln, natural logarithm of this amplitude. Are you following, right? The various amplitude you would get for various oscillations. You actually to count five oscillations and then determine the amplitude from the pendulum bob. Of course, you see, this is the setup. I cannot turn the camera right now. Okay, this is the pendulum bob, and in the life experiment. So this is the amplitude for various oscillation, counting from this 5 oscillation. Are you following, right? Whereas this lin AO is the initial oscillation, which is the oscillation you obtain when you have not started counting. Of course, in the method, the instruction, you are told to mark it at 50 centimeter. At 50 centimeter. Please do well to watch the live demonstration of the real practical. Are you following, right? This manipulation is just to see that we help some of you out in one way or the other. Like I said, whatever the manipulation, make sure you understand the experiment for what it is. On the D-Day, you will have no manipulation to survive on. I must be honest. I've said that in your experiment. I think M3 work. So we move on. Manipulative formula, shortest cut. Yes, here we have graduated above shortcut. We deal with shortest cut. Shortest cut for generating table of values. Question mark, question mark, question mark. So what is the shortcut to this? Now, before you are able to bring out the manipulative formula, I must say this and say it categorically clear. I'd said it in experiment M3 before now. You would have to run at least your first 2 experiments. Okay, let's say your first and or second experiment. So you can either run 1 experiment or you run 2 experiments. In this case, you have to run 2 experiments. There is a reason for that, because the first experiment starts with number of oscillation of 0.0. However, what I'm trying to do here actually is giving you this work in such a way that you don't even need to go and stress yourself running any experiment as it stands, because I'll give you the formula for what it is directly. And since this amplitude here is given as 50 centimeter, yes, in the manual, you can check it. The initial amplitude is 50 cm, that's a 50.0. Are you following, right? During that time, in carrying out the experiment, at this 50.0, you can evaluate lin AN. It's all about you getting your calculator and pressing lin 50. And lin 50 gives us 3.9120. 3.9120. 3.9120. That's the value of lin 50. Now, this lin 50 is our A0. You see this value? This is our A0, our A0. The intercept. Lin A0. What does it mean? Lin of the amplitude when your counting of oscillation has not started. So if we come back to this manipulative formula, I have lin AN. There are 2 quantities of interest for us here. This lin AN and N. Because according to the instruction, we are plotting a graph of lin AN against N. So these are the 2 variables. These are the 2 variables. Which means we ought to know the values of every other thing here. We should know the value of this guy. We should know the value of this guy. So that with these values, we can now start our manipulations to get the values of lin AN for any particular number of oscillation. Like I said, I'm giving you the formula directly. So let us go. Since our lin AN and N are the variables, we'll maintain them in the equation. It's just like in variation. When they tell you, find the equation connecting the variables. Find the formula, the relationship connecting the variables. Are you following, right? So I'm going to come over here. This first question mark is going to be lin AN, exactly the way it is in the theoretical equation. And then that is going to be equal to lin AO. This O here means when you have not started counting the number of oscillations. And if you read the instruction and as well watch the live demonstration of this experiment, which I did, like I said, that was yesterday night, so it's still less than 24 hours. You see the video in the live section of this channel. I already explained all of those, so you can check through to understand a little of what I'm trying to analyze here. Of course, you have to watch that video to guide you. So our lin AO is this value here, which means I'll remove this lin AO and fix that value 3.9120. Then minus the last question mark. We need to know the value of T over this tau. You know, this symbol is called tau in Greek. It's a Greek alphabet for T. But the meaning of this tau, all right, this symbol, the meaning of this alphabet in this experiment is relaxation time. Relaxation time, which is defined as the time during which the amplitude will decrease, you know, will become 1 over E, or approximately 37% of the original amplitude. All these amplitudes you are going to be getting from this oscillation of 5, 10 oscillation, 15 oscillation, 20 oscillation, 25 oscillation. But in the experimental procedure, you're meant to be doing them, counting 5, 5 oscillation, 5, 5 oscillation, 5, 5 oscillation. And for every 5 oscillation, you get the amplitude. So look at all the oscillations you're going to get from this second experiment, third experiment, fourth, fifth, and sixth. What time will these oscillations from the second experiment be equal to 1 over E, which is the same as 37% of your initial oscillation, of your initial amplitude? What time will the amplitude you get from here become what? 1 over E. That E is your, I think, natural logarithmic base. Is there your calculator with a value of 2.71 something? Yeah. You see it with the link key in calculator. But that 1 over E, if you convert it to percentage, is still the same as 37%. So the time during which the amplitude from the second experiment down will be 1 over E of the initial, or will be 37% of the initial, is what we call the relaxation time. And you should know how to get this relaxation time. You should know how to get it. You should know how to get this relaxation time. And I'm going to give you the value of this part. We already know the value of this capital T. We already know the value of this what? Capital T. Our relaxation time here is approximately 60 point something, 59 point something, 58 point something, 61, within that range. That is what the relaxation time would be. And somebody may now wonder, how did you get the relaxation time? And you are quoting these values for us. How did you get it? Do you know physics well from India? Yes, I do. How do you get that relaxation time to be that value? That is why I told you that you have to at least run the first 2 experiments. For this particular experiment, you have to run at least, look at this one, the second experiment, so that you can get the value of the amplitude, get the value of ln AN. Are you following, right? That is ln of the amplitude. Now, if you know your number of oscillations, small letter n, look at it, and you know the ln of the value of the amplitude, if you get the ln of the value, look at it, you fix it. I repeat, for this manipulative work, one has to know the value of this row at least. One has to know it. If you fix ln AN, for example, for this second experiment, when it was carried out live, the amplitude there was 44. So let's say 44.0. That was the amplitude, and I'll show you the value. Let's see if you can see this. Look at it for the second experiment, 44.0. This is the real value obtained when I carried out the live experiment. So with that 44.0 as your amplitude, you would find ln of the amplitude. And ln of the amplitude is this term here. So if I fix that ln of the amplitude here, which if you evaluate it, ln 44, that gave 3.7842 approximately. Ln of this guy is 3.4, let me indicate it, 3.7842. Remember, I'm doing all this to show you how the manipulative formula came about. That's what I've always told students. You don't just wake up and you copy things anyhow. See, there are basics for generating those values. Even in the manipulation, it is based on the real work. The problem in getting a manipulative formula here is this relaxation time. You must know it. You must. So that you divide this period for one oscillation by the relaxation time. Then fix it into this equation. You know your ln A naught already. And that will now become the manipulative formula for this experiment. So I just want to give you a little idea quickly on how you get the relaxation time. So using the value obtained for the second experiment, lane AN, which is this, gave us 3.7842. So if you fix 3.7842 equal to lane A naught is 3.9120. You fix it here. Minus the period. If you watch the live demonstration of the experiment, I explained how you could get, that period. The value is 1.59 seconds actually, where you are meant to displace the pendulum about 15 degrees and then count 20 oscillation. With your stopwatch, you check what will be the time for 20 oscillation. You are asked to do it for T1 and T2, but I always advise do only once. The second value will always rally around the first time. So if you get your T1, T2, add both of them, divide by 2, you get the T average. In fact, when we did it, we got something like, I think, I will still show you this because this, like I said, they come from the real work. You can see your T1, plus T2 gave us 31.8 plus 31.9, then divided by 2. Are you following right? When I carried out the experiment. So if we have 31.8 and 31.9 as T1 and T2, add both of them, divide by 2 to get T average. That T average, if you divide it by 20, you get 1.59. So that is how we got this period T. So if I fix up the value of lane AN for this second experiment, 3.7842 here, equal to lane A naught, which is 3.120, minus the period, which is 1.59, divided by the time, relaxation time, I don't know, times the number of oscillation for the second experiment, 5. You will get an equation which contains this. Let me show that. Lane AN is 3.7842, and then equal to lane A0, which is 3.1920, then minus 1.59, which is our period here, divided by the relaxation time, which you don't know, times N. And our N for the second experiment is 5. If you do this, you solve for this time, relaxation time. You solve for this relaxation time. The value will be around 58, 57, But if you are to carry out this experiment completely, you will find out an average of it. I decided to use 60. Whole number. 57 is approximately equal to 60. Are you following right? 57 is approximately equal to 50. 58, 59 is approximately equal to 60. Take your time and solve for this time. You would see that value I'm telling you about. So if the relaxation time in the nearest tens, because I approximated to the nearest tens, which gave us 60. I told you it's around 15, 58 or 59 point something. Approximate it to the nearest tens, you get 60. I decided to use 60 to generate that manipulative formula. If you understand all of these principles, somebody may decide to use 57 alone. The choice is yours. The main thing GMAETS 41 is emphasizing is that you must run at least 1 or 2 experiments before you can start thinking of manipulating anything. Yes. So with that, this is 60, like I said, approximately. Then you have 1.5. Having gotten my relaxation time, I repeat again, approximately 60. My problem is solved. I can now come up with my manipulative formula. That is actually how I generated this. Then we design experiment. If you understand the base of experiment and theoretical equation, you will love your physics work as you carry out your weekly practical. So we go. Now lane AN, which is one of our variable, equal to, I told you have to fix this value which you have fixed, lane of the first amplitude, then minus T. Our T is 1.59. Fix 1.59 there. The formula is coming out now. What people have been waiting for. 1.59, and then divide it by the relaxation time, which I told you in the nearest tenth is 60. If you decide to use 58 based on whatever you calculate from here, the choice is yours. The choice is not mine. It's yours. You still have approximate value. I've decided to approximate to 60. Then multiply by your what? N. Remember I told you in the manipulative formula, your two variables of interest will remain there. This is the relationship connecting the two quantities that you are asked to plot. The two quantities you are plotting are the variables. They are the variables. That is what you are checking for. That's what you are trying to determine values on here. They have given you the values of the number of oscillation. You are now to determine the amplitude for any 5 oscillation and then evaluate your lane of the amplitude. Natural logarithm of the amplitude. But take note, this is not logarithm. Take note, take note, take note. I guess in your table, this is log an base 10. But from the theoretical formula or equation, this is not supposed to be a log. It's meant to be lean. And I believe that will be corrected for you friends. So even that column, we already have log an base 10. Log an base 10. You can decide to change it to lean an. Are you following? Or you leave it and create a new column again for lean an. Follow the instruction from your laboratory technologist, whatever they ask you to do regarding that column. Because normally that column is not meant to be there based on the theoretical equation. That log an base 10 is not meant to be there. So either they tell you to correct it to lean an, or they might tell you, okay, evaluate that column with log an, then create a new column for lean an. Whatever they tell you is your business there in the lab. I've brought out the manipulative formula, please. I've brought it out. But I don't want to leave this thing with fraction, because if possible, if you can memorize this manipulative formula, good for you. You know that the first value is 50, where the lean of that first amplitude will give you this value, 3.9120. Okay? So I want to give you this formula in a way in which you can now memorize it so as to apply it in your laboratory. For that reason, I have to evaluate 1.59 over 60. So if I take 1.59 divided by 60, 1.59 divided by 60 gives us 0.0265. 0.0265. So I'm going to wipe this and fix 0.0265. At least you have seen it. You know where that single value came from. 0.0265, right? 1.59 divided by 60, 0.0265. 0.0265 n. So this is the manipulative formula, the shortest cut designed by the GMAETS 41, that any of you dear students in Unizik, as you are going for experimental work is 107, you know, those on Monday, I refer to them as sacrificial lamb for the rest. I was supposed to have done this work very well, but then Sunday was not funny for me. You know, spent the whole day in the hospital. Though not for me. There to attend to a medical emergency. All right? For someone, a dear Christian sister. So, that is why this could have been out on Sunday fully. But it doesn't matter, like I said, I have actually guided students very well on this channel on how to handle practical works. If you've been following GMAETS for the one step by step, you won't even have problems with this. You won't even need me to do this thing. You won't. But then you have done it. Now cram this thing, cram it very well for our dear students in Unizik working on this experiment this week. Those that are yet to run for Tuesday, I know there is not yet time for you to go to the lab. So if you know what is good for you, cram this value. All right? In performing the life experiment, well, like I said, it's interesting. I loved it, right? But it's tasking. It is tasking for you to determine the amplitude for every 5 oscillation in the process. Isn't funny. It requires complete vigilance. If you watch that video that I performed, the life experiment, you see I kept talking about it. And you see how stressful getting, the amplitude for every 5 oscillation was. But of course, I've helped you out. So thank me small. Tell me thank you from that end. Okay? As you watch this video, please make sure you share it. Share it as you are watching. If I don't wait to watch it to the end, immediately start sharing it to your friends, your classmates, your departmental WhatsApp group. Help somebody. Don't be stingy. Help someone. And remember, you can join GMAETS 41's tutorials. GMAETS 41 runs physical tutorial on campus. Are you following, right? Join GMAETS 41's tutorial. You can join either our physical class or our online classes. Contact GMAETS 41 in order to get the necessary details on how to register with us fully. Now, how do you use this formula? This is where it becomes messy now. We're going to use this formula to generate the rest value. We're going to use this formula to generate the what? Rest value. So let me teach you how to apply it, because in applying this formula, you are going to do a kind of feed forward, feed backward. Or what do I mean by that? How do you feed forward and feed backward? You have to obtain what I call a fake value, a false value of lin AN first. Use that fake value of lin AN to get the true value of AN. And then use that true value of AN to get the value of lin AN. Now look at it, let me show you. Now the reason for that feed forward, feed backward approach, like I've just mentioned, is because this lin AN is meant to be at least in 4 decimals, in 4 decimal place. Because this is a value we evaluated with calculator. So it's meant to be in what? 4 decimal place. If you don't apply feed forward, feed backward, you might be getting 2, 3 decimals and other things. And the number of decimals are meant to be uniform. So let us do that. Let us apply this formula. Get your calculator ready now. Get your calculator ready. For the third experiment, we want to evaluate our lin AN, the fake value. So quickly, you will have lin AN. That is when n is equal to 15. Is it 15 or 10? When n is equal to 10, number of oscillation is 10. What will be the amplitude of the simple pendulum bulb? Apply this formula. Lin AN will be equal to 3.9120, or simply 2, and stop there, minus 0.0265 times our n is 10, times 10. So you can see that. Calculate your lin AN. So you have to reach out for calculator. You have to reach out for calculator. 3.9120 minus, you have 0.0265 times 10. So let us see what we get. This is 3.647. Mind you, when I am done with this, you will compare with the real value I obtained when I carried out the life experiment. So if you follow up with your calculator, you get 3.647. This is equal to 3.647. That's the value of your lin AN. 3.467. If you like, you can use that value directly. If you like, you can use it directly. No problem. You must not feed backward if need. If you really don't want. The only thing is, if you're getting 3 decimals, the 4th decimal just attach 0. If it is 2 decimal, attach 0, 0. But I will still advise you follow what I'm doing here. Feed it backward. What do I mean? I'm trying to get an approximate value of lin AN. If I get it, I'll use it to obtain AN. That AN value should be in whole number because it is the position. Yeah, it is the position of the pendulum bulb as occurring out the experiment. That's the amplitude from the 0 centimeter mark of the meter rule. Okay? So, if this is the approximate value of lin AN for the third experiment, what will I now do? I will use this value to get my AN, to get it back. And how do you get AN from here? This is lin AN equal to 3.467. So to get an, you take the ln of both sides. Is it ln, or you take exponential of both sides? So this becomes an equal to exponential 3.467. So your an is equal to, evaluate exponential 3.467. Exponential 3.467. This is just calculator stuff, nothing. Exponential 3.467. So this gave 32, right? 467. So it gave 32. It gave 32. Are you following, right? And since it gave us 32, what do we have to do? You record the 32, no problem. 32. Are you there? Which means that the amplitude in this case will be 32. The amplitude in this case will be what? 32. And then you are going to get back the real value of ln an now. And the real value of ln an will now be ln 32. Ln 32 here is 3.4657. Once again, 3.4657. Therefore, true value of ln an is equal to 3.4657. 4657. This is actually the value in 4 decimal. You can see that in 3 decimal it was approximated to 6 with this value. Are we together? So we have obtained the values here. All we need to do is to fix the value here. In this case, this is 32. In the live experiment, it was 34. But no significant difference. No significant difference. Then ln an gave us 3.4657. You know, this is just for us to get approximate value of ln an, to help us get our an by taking the exponential of that approximate value of ln an. Once I get my an as a whole number, like I said, it should be in whole number. You can now get the true value of ln an for that particular experiment. When n is equal to 15, you repeat the same thing. When n is equal to 15, you repeat the same thing. I'm going to just press it directly, follow through with this example. There seems to be a mistake somehow here, right? Let me still evaluate this, please. Let me evaluate this. Seems like I pressed something wrongly. 3.9120 minus, then we have 0.065, 0.0265. Good. Multiply by 10. I'm evaluating this again. Let's be sure of what we got. This is meant to be 3.647, please. 3.647. 3.647. I made a mistake. No wonder this is giving me 32, but it doesn't matter. Assuming that was the value calculator gave to me, I will apply it. There is no significant difference from the original value, you know, obtained from the real experiment. But please, let's get the correct value as we have it. This is 3.647, not 467. And that is why I'm not getting 34, because in the real experiment, this is actually 34. Okay, we go 3.647. Like I said, if you like, you can fix that value here directly. The choice is yours. The choice is yours, but I didn't do that. And I'll advise you to use the feed forward, feed backward. What does it mean? Get an approximate value for ln an first, this one. Then use it to get your an. After you get the true value of your an, you can now get the true value of your ln an as you are meant to record in the table. So this is meant to be exponential 3.647. Exponential 3.647. Let me wipe this, please. Exponential 3.647. Let's see what we get here. Good. Exponential 3.647. With your calculator, if you evaluate it, you are going to get 38.359, you know. Pick your whole number, approximate to the nearest whole number. So that value is actually 38. The mistake I made there could have, you know, taken us to somewhere else. So please, this is approximately 38. So your AN is 38. I've gotten the true value of our AN. Therefore, I will now use the true value of AN to obtain the true value of ln of that AN. So let us evaluate ln 38. Ln AN will be equal to ln 38. And the result would be, let's check, ln 38. Ln 38. Good. So ln 38 gave 3.6376 approximately. You can follow up with your calculator, like I said, 3.6376 approximately. So let me write it, 3.6376. And you know you are meant to record this in the columns of your table directly. So simple. What will I do? I'll come to this third experiment with number of oscillation 10. Our AN value is 38.0, and our ln AN value for that experiment is 3.6376. 3.6376. So we are done with the first one. Let us now check the second one. That is the second manipulation when n is equal to 15. Remember, this is the formula I am using to generate the values. So cram this formula, please. Cram it. Don't write it on paper. Have it in your brain. Nothing is there. You can. With it, you might not need to run the experiment. You might not. Your first value here is 50. Your ln 50 is 3.9120, which appeared here in the manipulative formula directly. The other ones, you know, you have the values already. So substitute. If n is 5, fix 5 here for the second experiment. Work on it. You get the approximate value of ln AN. Use it to get AN, which will be 44 there. Then evaluate ln 44. You get this. Repeat again for the next one, which I've just done here. Okay, let us go to when n is equal to 15. Let us go for when n is equal to 15. I'll wipe this now and then repeat the same procedure. Remember, I did feed forward, feed backward. I got an approximate value of ln AN first. Then ln AN equal to that approximate value. Take exponential of that approximate value. You know, to remove ln, you take exponential. Take exponential of that approximate value and then get your actual value of AN. From that actual value of AN, get the true value of ln AN, which you have to record. So when n is 15 for this experiment, what do we have? Go back to this equation. You have ln AN equal to 3.1920, or simply 3.192. 20 is still the same as 3.192. Please let me manage up this space. Then minus 0.0265 times 15 times 15. I hope this has not cut off from your view. Let me check. Times 15. Okay. Times 15. So let us evaluate this and see. Our ln AN will now be equal to, with your calculator, you evaluate 3.9. This is 912. That's right. 3.912. Then minus 0.0265 times 15. This is 3.5145. 3.5145. Let's check again. 3.912 minus 0.0265. We are multiplying it by the number of oscillation 15 for the fourth experiment. And this is, the approximate value is 3.5145. Since this is in fourth decimal, one can decide to you know. Anyway, don't record that. Don't. Why you don't need to record this value directly is because the values you have here are obtained from ln of these amplitudes here. That is why I told you use the feed forward, feed backward approach. So with this approximate value of ln an, we can get our an now. An is for us to take exponential of both sides. You know, to get your an, you need to remove this ln. And to remove ln, you take exponential. Exponential of this ln an, the ln will disappear. You'll be left with an. Then you come to the right-hand side, take exponential 3.5145. Let's use that value and see. So exponential 3.5145. So this is what I got here. Our an is equal to 33.599, which you can approximate to nearest whole number. You get 34. You get 34, which means our an in this case is 34. With this true value of an, you fix 34 here. Are you following, right? 34.0. Then take the ln of this 34.0, which means that the true value of ln an will be ln 34. And ln 34, let's see what we are going to get. Ln 34. Ln 34 gave us 3.5264. So do you see, we didn't get this exactly. That's why I told you, use the feed forward, feed backward approach. You see, I designed this experimental formula. And of course, that's the manipulative formula that solves this if you don't want to perform the experiment. But then you see some things that I had to do. I could have been done with this class since. Just come, give you the manipulative formula, we'll start working on it, you know. I just tell you, copy. You go to the lab, do these things, and you're getting off values for this ln an. I have to take my time to explain this so you know how to apply this. And then using this opportunity to warn you against all this issue of shortcuts. So there are things you ought to have known. Not just giving you something like that. There are certain hidden facts. So it's always advisable you understand the practical for what it is. If you can perform it live, good. If you cannot, you want to rely on manipulation, then on your own, try to start coaching yourself. Because on the D-Day, there will be no way forward, like I said. And if you want to manipulate to get any manipulative formula, one of the things you want to take note of is you have to run the experiment live, either one or two. Then use it to determine what the manipulation will look like. Let us go to the next one. When n is equal to 20. That's the fifth experiment. When n is equal to 20. When n is equal to 20, you repeat the same procedure. Ln an will be equal to, you use the manipulative formula, 3.912 minus 0.0265 times 20. The manipulative formula of this equation, choke. It choke. That is why you don't see it anywhere. But one thing is, you say, I love you, friends. I really want you people to learn. And most times with all this physics experimental work, I'll just tell them, go and do the experiment. Understand how to carry out experimental works. It's for your good. If you happen to practice what you studied after you graduate, you will apply scientific knowledge to your works. So you just have to understand these things for what they are. But you see, if it comes to the issue of shortcut, here at GMAS 41, you know, this is where everything about shortcut ends. Yeah. We can go deep, and fetch that thing that you need. But I still believe in understanding the main thing. That is why I had to run this experiment live first, show you the demonstration. In case, you know, before bringing out this for you. So I thought about it over the night. I was like, this experiment is tasking, student might, you know, find it a bit tough, especially getting the amplitudes for different number of oscillation. So let's move on. So with this, let us evaluate our ln an in this case. So this is going to be 3.912 minus, open bracket, 0.0265. You know, you have to put this in bracket as you evaluate if you want to press once. then times 20. 3.912 minus, open bracket, 0.0265 times 20. So this gave 3.382. So this is the approximate value of ln AN. Use it to get your AN. AN is equal to exponential 3.382. 3.382. So that your AN will be equal to exponential 3.382. Remember, once you evaluate this approximate value of ln AN, don't record it here. It won't tally with the value of your amplitude. That's why you feed backward. Okay? Show that manipulation what they do now, right? So we have 29.4. 29.429, you know, and the rest. But that 29.429, if you approximate it to the nearest tens, you will get 30. So I can take an approximate value of 30. But even if you record 29, no harm. Even if you record 29 as you see it here, no harm. No harm. No harm. So feel free if you get anything like that. Can record that 29. In fact, let me fix it. Let me maintain it as 29. 29. But again, let me evaluate this. 3.912 minus 0.0265 times 20. So 3.382. Exponential of that 3.382, let's see once again, give us 29.49, you know. So I will use it. There is no issue. Therefore, our true value of ln AN will be for you to take ln 29. And if you take ln 29, you are going to get 3.3673. 3.3673. 3.3673 approximately. Transfer this value here. We have our AN to be 29.0, and we have this. We have ln AN there to be 3.3673. I didn't write the value of ln AN for this amplitude of 34. So let me evaluate ln 34. For this one, 3.5264. Then finally, when we have our n to be equal to 25, you repeat the same thing. Let's see what we are going to get. I think in the life experiment, this value, this fifth one, was actually 30. It was actually 30. But does it matter? 30.29 within allowable experimental error. Is it not accurate? And I tell you that it is accurate. Are you following right? It is accurate. You are not perfect. You're a human. You are not above mistake. Your experimental work can be subject to one error, you know, one or two errors as the case might be. That's why sometimes we determine error in slope and, you know, to handle the error analysis. So finally, when n is equal to 25, our ln AN will be equal to, you come back to your formula, 3.912 minus 0.0625 times 25. Times 25. I hope this has not cut off from view. I'm using this to track what is happening there. Okay, times 25. So it appeared. And with this, our ln AN will be equal to, we evaluate it, 3.912 and then minus 0.0625. And I have to put that in brackets. Minus open bracket 0.0625 times 25 times 25. And this gives us 2.3495. Remember, this is approximate value of ln of the amplitude for the last experiment with number of oscillation, 25. You are not to record this here. Don't. Use that value to feed backward. Are you following, right? And then later forward. So let us use this to get the true value of AN. AN will now be exponential 2.3495. And then your AN will be equal to exponential 2.3495. This gave 2.3495. So let's see. Once again, we have 3.912 minus open bracket 0.0625 times 25. 2.3495. Okay, so exponential 2.3495 gave 10.48. Gave 10.48. That is a wide range difference, right? As your AN, 10.48, which is approximately 11. It's approximately 11, right? Let me leave it as 10. You can say that. I'll leave it as 10. The value is quite below what I was expecting. But it still doesn't matter, like I said. It still doesn't matter. You know that as the damping is taking place, the amplitude is decreasing again and again, right? And so from here, we can now get our lane AN. Lane AN is going to be lane 10, which is 2.3026. So as long as these values are decreasing, I'm okay with it. I'm okay. And I've said that within experimental error, whatever you are getting, just let it follow that format. And that is cool. So here we have this to be 10. And then at this point, we have this to be 2.3026. Let's evaluate that finally. 3.912 minus 0.0625. We're multiplying by 25. And then it gave us 2.3495. And of course, can use it to generate the value of AN. Take exponential of that 2.3495. And once again, I'm getting 10.48. I'm okay. Approximate to 10, and then evaluate your lane AN, which give us 2.3026. So this is what your table of value will look like. This is what it will look like. However, I would tell you something about this value point, this 265. If you had used 264, the values will still fall within certain range. This last term will be there about 26 or so, if I'm not mistaken. Yeah, there about 0.0264. Then times 3.912. Then minus 0.0264. Instead of 265, 264. Then times 25. I am not saying you should go use 64. If you are to use 64, yes. Not around that, this was actually giving me something 264. But it still doesn't matter. I explained something to show you how we got this particular value. Okay? That last term could have been 3.252. Last term here could have been 3.252 this. And if you take the exponential, pay attention. If you take the exponential of that 3.252, exponential 3.252, you will be getting a value as exponential 3.252, right? Or 352. Let me work on it again. 3.912 minus, open bracket, 0.0264 times 25. Then I'm taking exponential of that time, exponential of 3.252. That gave 25.8, 25.8, 25.8, which is approximately 26. That is actually what I'm expecting here. Are you following? That's what I'm actually expecting here, 26. I don't know why this value went that low. I don't know why it went that low. But if that happens to be, it still does not matter. Our interest is that in the work here, the values followed a particular format. For example, the lin AN, you notice that the values were decreasing. And that is sufficient. That is sufficient. Perhaps you could use 0.0264 instead of 265. Yes, 0.0264 instead of what? 265. So let me fix all here. Let me fix this guy all minus 0.0264 and then n, which means it's going to be 3.9120 minus this. As we conclude this, I'm going to show you what the live demonstration of the experiment, the value that we got in the live demonstration. In the live demonstration. These are the values. Now you notice the second value is 44. Look at the board. You have 44. Then if you evaluate the link, you know what the value of that link would be. Your interest is to get your AN. Now the third AN value is 38. The third AN value is 38. Now look at the board. From the manipulation is still 38 when N is 10. Then the real experiment, the fourth amplitude value is 34 when number of oscillation is 15. Look at what we got in the manipulation, 34. If you evaluate ln of the amplitude, you get exact thing. There will be no difference because it's simply ln of your AN. Then when N is 20, number of oscillation is 20. Look at the value of amplitude we got, 30. Now look at the board, 29. If you approximate 29 to the nearest tenth, that is from here to here, you still get that 30. You still get that 30. Why you didn't get, the reason you did not get that 30 exactly as we have in the experimental work is because of this part. Because this is the approximate value of the slope. Like I said, we used 6.5 here. If you use 6.4, you will get that 30. Remember, when I was trying to get this time constant, if you work on it, it's around 60 point something, but I used 60 instead. It's actually 60.315. 60.315. But I used 60 instead. That is why this value gave us 0.0265 instead of 0.0264. But it doesn't matter. I've said this time and again. It doesn't matter. Now look at the last value. That's where, the value went quite low, like I said. And I explained the reason. But it still doesn't matter. 25. And then our AN is what? 26. But I'll advise you to use that 26. I'll advise you. There is still something I observe in the experimental work. And I've told you time and again that from my analysis, this relaxation time is 60.3125. Yeah, something like that. That's what it is. But we used 60 when I was, trying to calculate this to get an approximate value. I used 60. That is why this gave us 265. If you were to use 0.0264, you will get exactly the values in this work here. You'll get these values. You'll get them. But the choice is yours. All I'm interested in is just to show you how you apply this formula and then show you how you get these readings. I am not interested, finally, in any single value that it kind of goes away from what I am expecting. It doesn't matter significantly. This is experimental work. Who told you in the life experiment, that I didn't make mistakes there? At least while the work was going on. It's possible. I am a human. You too, you are a human. There is every possibility that you could make certain mistake while performing the experiment. That is why I had to make sure I actually release this. Are you following, right? Because the experiment is actually tasking to know all those amplitudes, because you are not allowed to stop the oscillation. The oscillation will be continuous, and then at every 5 oscillation, you quickly take note of where the pendulum bob is, giving you the amplitude along the length of the meter rule. But cool, like I said, you've seen this, and I've told you what may have likely happened here. I would just advise for this last value, based on what you've seen here, even if you memorize this and you apply it, for this last value, please, just for us to be a bit consistent, use your 0.0264, which will give you this to be 26 or thereabout. But let me even shock you. Let me tell you something. In the instruction, the method, read it. For you, the 6 students that are dealing with this experiment, read the method. Find out that you were told to carry out this experiment until the amplitude gets to 10. Until the amplitude gets to what? 10. Which, of course, is what this last value is giving me. Instead of 26. It's there in your manual. So, do you see? But, my dear friends, as I conclude this, don't worry. Whether you want to use that 0.0264 such that you get your 26 here, the choice is yours. If you said, no, it doesn't matter, I want to maintain this 10 here, the choice is yours. You commit no error. Your table will be marked fully. Because, of course, you're a human. But one unique thing about the table of values is that it follows a particular format, which is, it's decreasing. It's decreasing. Yes, the difference from this to this, that is from 50 to 44 is 6. The other one tends to be 4, 6, 4, 5 in that order. Then this one decreased there about 19 or so. And of course, we really expect that, because you don't expect the decrease to be all uniform. You don't. What if there are factors that are affecting the damping? Assuming during the last experiment, there is an environmental factor that caused friction to the pendulum. You won't be aware of that, thereby slowing the pendulum bob faster than usual. It's possible you still get this. I'm emphasizing on all of this so that you'll be confident that yes, this works perfectly. And with this, you can plot your graph, plot a graph of lane AN against N. If you plot your graph of lane AN against N, you will get a negative graph. How do we know that you will get a negative graph? Look at from the theoretical equation, this T all over, that is the period all over the relaxation time, minus the period over the relaxation time is your what? Slope. Since that is the quantity multiplying what you are plotting on the horizontal axis. And if you look at this quantity, it is negative. Therefore, your slope will also be negative. The shape of the graph will be something that looks like, let me just cast it here. It's something of this kind. Just describing all of them. I mustn't plot the graph. I've done a lot of graphical works for you. Though I'm going to release the last part of this particle later today. Definition of all those terms. But those definitions as well, you can just Google them. Nothing is there. What's the definition of relaxation time? Time taken for the amplitude to become 1 all over E, or 37% of the original amplitude. All right? You have to calculate your damping coefficient B. B is equal to 2 times mass divided by the what? The relaxation time. Are you following right? And the mass of the pendulum bob will be given to you in your lab. Like this one, when I measure, is approximately around 20 gram. You convert it to kilograms. So this one just requires your basic knowledge of mathematics. So this is how the graph will look like. To take your slope, sometimes students have problem with taking negative slope. The slope will go this way. The slope will go this way. Are you following right? You can decide to come to this point and this point, of course, and then rid of your value. The graph is sloping down. The graph is coming from top down. The initial point will be that top, and the final point will be the down. So here is your initial point, initial point, and here will be your what? Final point. With this, you can now trace, this is your lane AN, the vertical axis, and the horizontal axis is your what? Lane, is your N rather, is your N. The slope does not have unit, take note. So it is a dimensionless quantity. Okay, it's a dimensionless quantity. It actually represents the logarithmic decrease, in the oscillation, the amplitude of the oscillation. The logarithmic decrease in the amplitude of the oscillation. That's what the slope represents. I think you're asked to actually state what the slope represents. Okay, in getting our slope from the graph, you come to this point, take it from that point here to the vertical. Take it to the vertical. So here you read off your value. That will give you the initial value on the vertical axis. Then on the horizontal axis, take it down from that point, dot, 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 dot. This is the initial value on the horizontal axis. This is your LN lane AN1. Lane AN1, the initial value on the vertical axis for the slope. Then this is your N1, the initial value on the horizontal axis. This is the final point. Come to the final point and do the same. Get the final lane AN1, AN2 in this case. Are you following, right? And how do you obtain it? You trace from this point, dot, 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 dot. It will come out somewhere here. And then from here, take it to the horizontal, dot, 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 dot. It will come out here. So what I'm talking about is that this is your N1, this is your N2, this is your lane AN1, and this one is your lane AN2. You know that the value of the initial on the vertical will be greater than the value of the initial on the horizontal. Are you following, right? To be greater. The initial will be greater than the final. So that if you do the final minus the initial, you get a negative result. Anyway, I would release the video, like I said, on that. I'll release it, just quick thing to look at it. Then the definition of those terms. Now, once you get your slope from the graph, it will be negative value. Like I said, your lane AN1 will be greater than lane AN2. Because the final point of the vertical is here. The final point of the horizontal is here. So if you take that of the vertical, you have the value here. You take that of the horizontal, you have the value here. The initial point is on top. Take it here, you have the vertical value. Take it down, you have the horizontal value. The initial value of the vertical will be greater than the initial value of the horizontal. So if you take the difference, final of the vertical minus initial of the vertical, it will produce a negative result. And then you divide by N2 minus N1. In the case of N2, N2 will be greater than N1. Do the subtraction. If you work it out, you'll get a negative result. Equate that negative slope to negative period over relaxation time. You know your period already. Period is 50. Is it 50? No. Period is 1.59. Yeah, period is 1.59. Your slope, if you evaluate it, will be approximately minus 0.0265, minus 0.0264, within that range. If you work on the slope of this guy. So you equate that slope to minus period over relaxation time. You don't know the relaxation time supposedly. Forget about this manipulation that I've done to get it. So running the experiments, assume you don't know it. You have to get the value from the graph. So the slope you obtain, which I say is approximately minus 0.0265 or minus 0.0264, equate it to minus period over this, which means you're going to have something like minus 0.026, let's say 4, equal to minus 1.59 divided by the relaxation time. Calculate the relaxation time. If you solve this, you get there about 60 point something. Let's even find it out. Get there about 60 point something. 1.59 divided by 0.0264. So this gives 60.222. You can say that. Already from the manipulation and other things, we've gotten what the values you are meant to get from the slope would be. So when you are working on it, you see how the values are coming out. Okay, let me use this as the value of the slope. So I'm using minus 0.0265. So it's going to be 1.59. You know, the negatives we cancel. Divided by 0.0265. It gave exactly 60. It gave exactly 60. That will be the value of the relaxation time. Okay, so let's say approximately 60. The unit is second. The unit is second. Your slope, if you evaluate it from here, like I said, it will be approximately minus something of this range, 0.026, 2 something. Then from it, use it to determine your what? Time, relaxation time. Because minus period divided by relaxation time is the slope from the theoretical equation. So you equate the slope you get from the graph to your minus period all over what? Relaxation time. Calculate your relaxation time, you get 60. So that is it. To get your damping coefficient is simple. Let me wipe this. To get your damping coefficient is simple. Let me indicate what the slope would be here. Slope will be approximately, let's say 0. Let me say equal to 0.0. Equal to 0. Oh no. Just giving a rough value of this in case I'm not able to put out anything again. 0.06 be 0.264 or 5. Let me leave it at 5. Let me leave it at 5. I commit no crime. Okay? Whatever you get, you fix it there. Now you're asked to calculate the damping coefficient. Damping coefficient B is equal to 2m divided by the relaxation time. And then your B will be equal to 2 times. Remember I told you the mass, when I measure the mass of the pendulum bulb, is approximately 20. It's approximately 20, and I can use that 20 grams. So you have to convert it to kilogram by dividing it by 1,000. So in the denominator, I'll divide by 1,000. The relaxation time is 60. Then times, remember I'm dividing 20 by 1,000 to get my what? Mass in kilogram. If you do that, the damping coefficient is going to be equal to 40 divided by, the denominator is going to be 60,000. 60,000. And this gave 6.67 times 10 to the power of minus 4. 6.67. 6.67 times 10 to the power of minus 4, which is the same as 0.00067. Is the same as this. And what is the unit of this damping coefficient? If you look at it, this is mass over, a time value, because we call this relaxation time. The SI unit of mass is kilogram. So it's going to be kilogram per. The SI unit of that relaxation time is second. So it's going to be kilogram per what? Per second. Trying to find out that nothing cuts off here. Okay. Now we have obtained our what? Our damping coefficient. We've obtained our damping coefficient. Remember that in the manual you are also required to determine, I think, the quality factor. The quality factor Q. All right. Let's see if I can work it out somewhere here. Let me wipe this, right? You can still manage this space. Quality factor, that's the next thing you have to find. Quality factor Q. And the formula was given in your manual if you read through. The quality factor is the natural angular frequency multiplied by the relaxation time. I've defined the relaxation time severally. The time it will take for the amplitude of the oscillation to be 1 over E. 1 over small letter e, that's the base of natural logarithm, all right? The time it will take for the amplitude to be 1 over e, or 37% of the initial amplitude. That's the definition. You were asked to define it, and that's why I kept emphasizing on it. So all you have to do is to substitute. We know the value of our natural angular frequency, 3.95. Please take note, the unit of this is radian per second, not any other thing. This is not ordinary frequency, please. If you have taken your lesson on circular motion, because that's the introductory part where you start meeting all this angular velocity, you know, all these circular quantities, rotational dynamics quantities, simple harmonic motion quantities. This is not ordinary frequency. It is called angular frequency or angular velocity. The unit is radian per second. These 2 pi actually represent angular displacement, and it has the unit radian. Remember, your unit is very, very important. If you write a wrong unit, you fail something, the mark will be subtracted. So we're going to fix that value 3.95 and then multiply by the relaxation time, which is 60. If you work on this, let's see what we are going to get. So 3.95 times 60. And this gives 237. 237. 237. Now, what would be the unit of this? What would be the unit of this? Remember, the unit of this angular frequency, natural angular frequency, is radian per second, which is radian divided by second. Rad divided by second. That's the unit of natural angular frequency. And it is multiplying our relaxation time here. SI unit of relaxation time is second. So mathematically, this second and second will cancel out. The second will cancel out. So you'll be left with what? Radian, rad. So the SI unit here is rad. 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 Which means that the quality factor is actually dealing with the angular displacement. That quality factor, which is omega t, natural angular frequency, okay, times the relaxation time. That quality factor, suppose you are asked, what does it represent? It's actually the angular displacement, yeah. The natural angular displacement of that oscillating system, our pendulum bob in that case. Take note of all these things I'm saying. Like I said, I must not, you know, write out everything on paper, on the board and other things. See, you are being built to be confident in yourself. I keep singing this on the D-Day. Listen, it will be you and you in the exam hall. Use this time to learn all the things you need to learn, the way you are meant to learn them. Make note of all these things. I might upload a pre-recorded video on this stuff, maybe much later if I have the time, because my time today is really tough. But I just quickly have to run through all this so that you can be able to follow through in case. So you see how I've established that the SI unit of our quality factor is what? Radian. And since it is radian, it's actually defining angular displacement. Under circular motion or rotational dynamics, that quantity we use theta to represent, theta. And you remember that omega, angular velocity, is equal to theta divided by t. In fact, I love this experiment. I love this experiment. Kudos to the Unizik lab technologies team that designed, you know, this experiment, at least for the first time. Let students move into something real. We used to study the theory of all these things, circular motion, simple harmonic motion, you know, damping, damped oscillation, and the rest of them, forced oscillation, free oscillation. Performing the experiment, you know, is really ideal. So I love it. What else? We are done with the quality factor. Okay, I think the next thing you were asked to define is a free oscillation, forced oscillation, and damped oscillation. Yeah. What is your free oscillation? It's a type of oscillation where a mass, a particle, oscillates at its natural frequency. it does not depend on any external driving force. So the type of oscillation in which a system oscillates at its natural frequency without an external driving force is what we call free oscillation. Remember, at the end of this class, a copy of this live class will be made available, so you can still check back, listen to all these things. You are really learning and teaching you this for what it is, so you have the whole idea of this experiment. We've defined free oscillation. The next thing, forced oscillation. Forced oscillation. It is the type of oscillation where a system oscillates at the frequency of an external driving force. The type of oscillation, forced oscillation, just imagine, forced. It means you are forcing that system to oscillate. Something is trying to force it, an external force. Remember in the first one, free oscillation, nothing is forcing it. On its own, that system, that pendulum bob, whatever the case is, will oscillate on its own naturally, using its natural frequency to oscillate, using its natural angular frequency to oscillate. But in the case of forced oscillation, a system oscillates at the frequency of an external driving force acting on it. You get that right? And then for damped oscillation, it is defined as a type of oscillation in which the system loses energy. The type of oscillation in which the system does what? Loses energy, and the amplitude gradually decays. And the amplitude gradually decays, which means the amplitude gradually decreases. That is what our damped oscillation is. And of course, that's what we did here. You notice in the live experiment, are you following? Yeah, you can watch the video. You can watch the video where I demonstrated a live experiment. Under the live section here, you would see that video lesson. And that is what we demonstrated here. The amplitude keeps decreasing, keeps decreasing, keeps decreasing, keeps decreasing. Okay? So the system is losing energy. That is why the maximum displacement from its rest position will start reducing with time, with the number of oscillation. We are done defining what damped oscillation is, forced oscillation, and free oscillation. I think the last thing, if I'm not mistaken, you were asked to state the significance of the slope. What does the slope represent? The slope of this graph, what does it represent? The slope of the graph is a dimensionless quantity. The slope of the graph is a dimensionless quantity, which represents the logarithmic decrease, which represents the logarithmic decrease, and it measures the rate at which the amplitude reduces. It measures the rate at which the amplitude decreases, reduces with time. Is that clear? Although here we dealt with it with respect to the number of oscillation. So all you just have to write is simple, that for this experiment, the slope is a dimensionless quantity because it does not have a unit. It doesn't have a unit. Are you following? It's a dimensionless quantity which represents the logarithmic decrease in oscillation, in the amplitude of the oscillation. And it measures the decay, the decrease, the gradual reduction in oscillation of the system. I wish you all the best in your practical work. Please, like I say, share this video to your friends. You still have those that are going to do the experiment later today, tomorrow being Wednesday, likely Thursday, and Friday, whatever the case is. Some persons, if care is not taken, theirs might even be carried over to January next year. Well, I'm not the one to decide that. I don't have that right. Your lab technologies decide all of this. At the end of everything, please, do not stop your learning at copy and paste. Give me, let me write. I don't like that. It's not for your good. I always say that. That is why oftentimes if I come on live to teach certain key things, I would always try to show you what you need to know. I will expose all the secrets. Because one day, GMAETS might no longer be there for you. And of course, that will happen towards the end of the semester when you sit for your examination. I will not be there because I would not know what your examiners are going to set. Am I communicating right? I would not know. It will be you and your question paper, your apparatus, and of course, if you're asked to carry out the life experiment, you perform it. And even if it is an alternative to practical, and your examiner decides to give you your theoretical equation guiding that experiment, you've got no choice. And GMAS is here and has been helping you and will still continue to help you to understand the implication of theoretical equation. I have actually taught that time and again. Are you following right? Make sure, please, you understand your theoretical equation and the implication. I have a unique video lesson that deals with that. At the end of this video, this live class, I would post, I will add the end screen to read so that you can still click and go back. It is for your own good. Learn the importance of theoretical equations. So share this video. If you have not subscribed, please make sure you subscribe right now. The effort that goes into making these videos available is not easy. I'm live teaching this right away, bringing out everything, exposing all the secrets to this practical work, not just for this particular experiment, but what will guide you even through into your exam. And of course, anytime you're dealing with physics practicals and graphical works and the likes, comment as much as possible of appreciation on this video and share it to your friends. Encourage them to watch. Mind you, as I round off conclusively, I did not hold this live class just to release a so-called manipulative formula. Go and then you do your experiment get your values without carrying out the experiment. That's not the main reason why I did this live. Because I did it to give you the formula, no argument, but again to teach you and continue opening your eyes, raising your conscious awareness on the importance of theoretical equation and on the importance of you as a student to understand how to apply this guide. It's going to help you a lot as you move on, not even only in your 100 level, in higher levels. You will love this. You will remember GMAS 41 and you will appreciate so much. But don't wait until then. Start appreciating GMAS. Share the video. Become a channel member. For those that need physical tutorial music, contact GMAS 41 to get information about our physical tutorial. If you've not joined tutorial yet, you're waiting until January, feel free, then contact GMAS 41. Over the break, you can also contact GMAS 41 to do your registration ahead of January. It's going to be very hot, very, very hot from January. So act wisely now. Hurry and register. I'll be seeing you friends much later. Like I said, I'll try to release a pre-recorded video on all these definition stuff just for it to be there for you to see. I've defined them. You could just write those terms out. And GMAS 41 has his physical tutorial in Unity Campus today by 4 to 6. All right, we are taking on 101 today. Make sure you look for us and join the tutorials, okay? Wish you all the best. Take care of yourself.